Yeah, so I am on sabbatical here at CMU until the end of December. So if any of you is interested in talking with me about work, this or any other work, I will be happy to do so. And this work that I'm going to talk about today has been done with my student Weiran Wang, and most of it is unpublished, but at the end of the presentation I will give you some pointers to preprints. Okay, so the topic of the presentation is learning nested systems. I'm going to explain what I mean by that. I call a nested, or you can call it hierarchical system, essentially a sequence of processing layers. For example, in computer vision, you have object recognition pipelines where you start from the image and then you apply processing such as extracting features, like shift features. Then you may do sparse coding, pooling. At the end, there may be a classifier that outputs a label for a given object. In speech, you may have a phone classification pipeline, works similarly. You have some features that you extract, such as MFCCs, and eventually there is some kind of classifier. In machine learning, we also have similar things for regressional classification, where you take your input and then you apply to it some kind of processing, such as PCA, to reduce the dimension, and then after that you apply a classifier, for example. And another example are deep nets, where you start from a given input, then you apply to it a linear layer followed by a nonlinearity, like a sigmoid. Then to the output of that, you apply again another linear layer and a sigmoid, and so on until you get the input, you get the output. Okay, so I call these kind of systems nested systems, because what I mean by that is that mathematically they construct a nested function. So the input is here, and you apply a function, then to the output of that you apply another function, etc., until the last function gives you the output that you desire. Each of these layers is going to have trainable parameters that I call here weights, and each layer performs some kind of processing that gets more and more sophisticated as you go down the pipeline or the cascade. For example, in computer vision, often you start from the pixels of the image, and then there is a first layer that is going to do some filtering and extract, for example, edges. Then after that, you may get T-junctions, parts of objects, etc. And those are ever more abstract and sophisticated representations of the image, which are often inspired by biological processing. Okay, and in all these systems, these nested systems, the ideal performance is obtained when you train the parameters at all the layers jointly towards the goal that you want to satisfy, such as classification error, for example. And this presentation is purely about how to do that efficiently and easily. It is not about designing nested systems or neural networks. It is about how to train them efficiently. Okay, I'm going to do now give a little background on shallow versus deep systems. Shallow systems conventionally are systems that have either no hidden layers or just one hidden layer, and basically they are easy to train. For example, a linear function or a linear SVM or a lasso, that is something that goes practically directly from the input to the output, and the thing is that you can train that easily because the problem is convex. In some cases, the problem is not really convex, like for example, if you use a radial basis function, like this one here, which takes your input, passes it through a nonlinear layer of Gaussians, let's say, which are located at different centers. And then after that, you apply some linear weights to average, to combine those outputs. Then this is a nonlinear and non-convex function, and when you put it inside a loss function, such as the squared error, you get something also that is non-convex. But however, very often, we train this in an approximate way that makes it very simple. For example, if these are Gaussians, to train the centers of those Gaussians, what you do is you just run k-means on the input, fix the Gaussians, and then train the weights, which are linear. So in that sense, this model here can be trained very, very simply. Another example are support vector machines, where these will be the basis functions that are centered at the support vectors. And the support vectors, even though they appear non-linearly here, they can be obtained by solving a quadratic program in closed form. Sorry, not in closed form, but with a unique optimum. Okay, so these models are convex, they are easy to train generally, and they are also useful because either they are very robust models like linear mappings, or if they are non-linear, you can control the flexibility or the power of the model by changing the number of basis functions that you have here. And they are easy to train because usually they don't have local optima, either because they are convex or because we follow one of these approximate ways of training them. And then you don't have to use nonlinear optimization, which can be complicated. You just use either an eigenproblem or a linear program or something like that, which is easy to solve. Okay, and then deep systems are systems that have more hidden layers, more than one. Examples are deep nets, wrapper regression or classification. I will explain what that is in case you have not heard that. Or the pipelines that I mentioned in computer vision and speech. These systems, truly nested deep systems, these are nearly always non-convex because the composition of non-convex and the composition of functions gives you most generally gives you non-convex functions. It's hard to get a convex function if you combine multiple functions by composition. These models are also practically useful. They give you very powerful functions depending on the number of layers, etc. They may be better than shallow systems. There is right now a debate about the good and bad things of deep systems versus shallow systems. I'm not going to get into that. But the big problem that they have is that they are difficult to train. Firstly, they have local optima. That's not something I'm going to talk about today, but it is a problem. And the other problem is that they require nonlinear optimization or some kind of suboptimal approach, and that's what I'm going to address today. So let's look at how does one train a nested system, how that is being done today. The straightforward way is to use the chain rule, to compute derivatives of all your parameters on the whole network by applying the chain rule layer by layer, and that is called backpropagation, backpropagated gradient. For example, here, if you have a function that that has two functions here, f and g, then the gradient with respect to g would take this form here, and the gradient with respect to f would take this form by applying the chain rule, where you need the derivative of the first layer and the second layer. Okay, and this, of course, is very well known, and it works mathematically, in that you can compute those derivatives and then apply a nonlinear optimizer, such as gradient descent, or LBFGS, or Newton's method, or whatever you want. And indeed, it was a major breakthrough in the 80s when this allowed people to train deep networks, which were otherwise, it was not clear how to train them. It does have important disadvantages, though. Firstly, of course, you need derivatives. So your layers have to be differentiable, all of them, in order to apply the chain rule. Even if the derivatives do exist, then computing the gradient, these gradients here, can be difficult. I'm not saying it cannot be done. Of course, it can be done. But it takes a lot of effort to write down the equations, to vectorize it, to put it in matrix form so that you can put it into MATLAB, for example, and eventually to run it and debug it. If you have done that, it is quite cumbersome. And then when you have the gradient, then you have to apply nonlinear optimization, which is, depending on your level of expertise, it may or may not be very easy to get a method to solve your problem, to solve it efficiently. And then you have also the problem of vanishing gradients, which was noticed in the early days of neural networks, which consists of the following. If you have, like here in this net here, this is the input and this is the output. If you change a little parameter here, a weight, then that has an instant effect on the output and therefore on the error function. But if you change a parameter a little here, then because it has to go through this squashing nonlinearity here, which controls the variation in between 0 and 1, let's say if it's a sigmoid, and then that again goes through here through another nonlinearity, etc., then what happens is that typically the variation here gets damped exponentially, and then at the output there is very little effect. So what that causes is your gradients to be very poorly scaled, with some components being very large and some very small, and that gives rise to very poor properties for optimization. Your objective function is going to be ill-conditioned, and then even if you use second-order methods that have high-order convergence properties, they are going to move very slowly, following some kind of complicated path in your parameter space. Okay, and this was a big problem with neural networks in the 80s, and it was very difficult to train anything with more than 1 or 2 layers at the time. Okay, That's one way of training deep systems, using the gradients. Another way, which is sometimes not recognized as such, but it is what actually very often is done in practice, is to do some suboptimal training where you train the layers one by one, sequentially, and you fix them, and that's it. Of course, this doesn't give you an optimum. It doesn't converge to anything, it's just a one-time pass. It gives you a reasonably good solution, sometimes very good, sometimes not so good. It is fast and easy, and sometimes, particularly with neural networks these days, this procedure is used to initialize the parameters of the whole network, and then you refine them using backpropagation. That gives you a good starting point. Examples of that are the unsupervised and supervised pre-training techniques that were introduced in the last few years in deep nets, and also the way that you train a radial basis function network with Gaussians, for example, where you first look at your input only, do k-means there to compute the centers of the Gaussians, fix them, and then once you have fixed the first layer of nonlinearities, then the second layer is just linear, and you train that. So that's a sequential training, which is a form of unsupervised pre-training, and it works quite well. I myself train radial basis functions that way. Sure, it is not optimal, but it gives pretty good results, and you don't have to worry too much about the optimization. Okay. Following on this, there is in machine learning the terminology filter versus wrapper classification. What this means is, for example, if you have a mapping of this form where G is a classifier and F is a function that does some pre-processing on your input, think, for example, of X being an image and F being PCA, that reduces the dimensionality, and then after that you do classification, then this is a nested mapping, and ideally you would like to train G and F, that is the classifier, and the projection jointly to optimize the whole thing. Okay, but that's typically not what is done. What is typically done is that first you do PCA, you fix it, then you train your classifier, because it is very simple, even though it is not optimal. That is called the filter approach, in that this behaves like a filter that you fix, and then you do the classification, you train the classifier. You don't have to do it in an unsupervised way, like PCA, for example. You can do it in a supervised way, where when constructing F, you look at the labels, you do LDA, for example, linear discriminant analysis. That will work better, but still it is not optimizing F for your particular classifier G. If you want optimal performance, you have to train both of them at the same time. So these approaches, these filter or layer-wise approaches, they give you suboptimal results, which may or may not be good depending on the problem. What you would like to do is to train F and G jointly to minimize the classification error, and that's called the wrapper approach. But this is rarely done in practice. It is the optimal thing, but it is rarely done in practice, and the reason is the same reason why backpropagation is difficult. So you have to compute your derivatives with respect to F and G. You have to apply then a nonlinear optimizer. The optimization is going to be slow, etc. Also, you have the problem of local optima, which can exist. This, for me, however, is not really much of a problem. At least I don't consider it as a terrible problem, because what you can do is you can always run, for example, your filter approach or any way that you want to train the whole thing easily, but suboptimally, and then you initialize from there the joint optimization. You're going to get a better result. So the local optima for me is not really such of a problem. The optimization itself is more difficult, though. Okay, and then finally there is one other thing that has to be done, which is the model selection, the selection of the architecture of the model itself. That is, how many hidden units you use, for example, in each layer, how many layers you use, how many basis functions, how many components in PCA, etc., all these kind of things. And to do that, you need to do a combinatorial search by basically trying the whole model, training the whole model for a given choice of architecture. You train it, which is, as I said before, difficult. And then you repeat that for various choices of the hyperparameter, like the number of hidden units. Then you pick the best one. That's a combinatorial space to search, where each search is very costly because it has to optimize an entire deep net or an entire nested system. And this is approximated in practice, usually by either just training a few models. So by sampling this space, everybody does a little grid in the number of units and this or that parameter. So they pick a few values there, more or less cleverly, and they train them, and they pick the best one. Or simply, they really just fix the layers by hand, particularly with longer pipelines, like the computer, object recognition pipelines. Really, the layer, or in speech, those layers are really fixed by hand. And that was done a long time ago, and not many people fiddle with the details there. So in general, this is a difficult problem that is really solved by hand. It's more of an art than a science, and it is very costly. And in summary, then, nested systems, they are all over the place in machine learning and computer vision. They are good. They solve important problems. They are intuitive in that the reason why they are used is because they make something meaningful. Like, for example, doing PCA before classifying makes sense in that it is going to simplify the complexity and also denoise the data a little. So it is something that makes sense to do. But then you end up with these systems that are difficult to train. And you can do it layer-wise or with backpropagation, but these are all, they have problems. Okay, any question about this brief background? Then I'm going to introduce the main topic of this presentation, which is an algorithm that I call the method of auxiliary coordinates, which is a general strategy to train this type of systems. The algorithm, well, it's not really an algorithm, but a meta-algorithm, like EM. So it is a technique that takes your problem and is going to derive from there a specific algorithm in a certain way. The algorithm eventually comes out very simply, and it tends to look like the layer-wise thing that I just described, but corrected with another step that coordinates the different layers, so that the convergence is guaranteed. And also, the steps that you're going to get, the iterations, are embarrassingly parallel. So they decompose into separate subproblems. And the basic idea to do this is as follows. You take your nested problem, and then you're going to turn it into another problem which is constrained and operates in an augmented space with more parameters. So it's a problem transformation. And then we optimize over all those parameters, which are the original ones, so the weights, for example, and the new ones, which are the auxiliary coordinates. You optimize that constraint problem using a penalty method, and then the objective function that you get with the penalty, that one you optimize it using alternative optimization. And then the result is a sequence of steps that train layers and that coordinate the layers. So let's see how that is done. I'm going to introduce the idea for simplicity with just a single hidden layer. So we have only two functions, f and g. It applies more generally, but this simplifies all the equations. And also I'm going to use the least squares error. Again, for simplicity, you can use other loss functions. So let's consider then this problem here, which is just a regression problem of inputs x and outputs y that goes through these two functions. And each of them have their own parameters. So when I write here that the objective function depends on f and g, what I mean is it depends on the parameters of those functions. That's just notation to simplify so that I don't have to write here widths, bandwidths, or weights, or this or that, biases, etc. Okay, so this is the nested problem that we have. We want to optimize with respect to the parameters of all the layers, and we want to find a local minimum of that. Then what we do is the following. First, I said that we transform the problem by introducing auxiliary variables and turn it into a constraint problem. We do this like this. The auxiliary variables are these ones that I call set here. We introduce one variable, one vector of variables per data point. And it is here. So what we do is that this f of xn, which was inside here, right, that thing here, which is a deterministic function of f, whatever f is, whatever x is, that's a number. Okay, I make that a parameter, a free parameter. And then I take it out and put it as a constraint down here. Okay, so here is the constraint, and I say that f of xn has to be equal to that set n, and then set n goes here. Intuitively, this looks like the original problem. It looks to be equivalent to it, but it is a different problem. It looks like a more complicated problem also. But there is, you will see there is a reason why I do this. Okay, so now the problem is a constraint problem which has for each data point here, it has one of these constraints. These constraints are themselves several constraints because the output of f is multidimensional. And then we optimize this problem now over the original parameters of the functions and over the auxiliary variables, the auxiliary coordinates. Okay, so then the question is how to optimize that. At first sight, you might say, well, I see that set equals that, so I just eliminate it, but then you go back. So that's not what I do. Instead, I use a penalty method to optimize that constraint problem. So you see that the constraints come up to the objective squared. This is an error, a violation of the constraint. It comes up into the constraint squared. And I multiply that times a penalty parameter. Okay, so again, I have here my objective function, and then each of these constraints comes up to the objective squared times a penalty. And then I have this problem, which again now is unconstrained. And it involves f, g, and z, and this penalty parameter. Okay, this is a standard way, one particular way of training, of solving constraint problems using penalty methods. This is, in particular, this is called the quadratic penalty method. You can also use the augmented Lagrangian, which would look identical to this, but it will have this other term here, which is what makes the augmented Lagrangian. You have a question?
Do you divide by 2 for good luck?
I divide by 2 here and here so that the derivatives cancel that later, but yeah, it's not really, yeah. Okay, so the augmented Lagrangian here will have this extra term, which is not there, involving estimates for the Lagrange multipliers, but you can see that this is no more complicated than this here. It's basically this linear part there. So anything that you can do here, you can do it here. And then in the presentation, I'm just going to focus on the quadratic penalty because it is simpler to explain. This is better, though. The augmented Lagrangian, of course, is a better method than the quadratic penalty. Okay, then we have this function here, and what have we achieved by doing this problem transformation? We started with the nested problem here, and now we have this one here involving these extra parameters. And what has happened, basically, is that we have split through here the nesting of the function. So that nesting that had one function inside another one, now they have broken into 2 parts which are additively separated. We have here the last layer, which depends on this set n here, which is a parameter. It takes values. And then we have this, which is the first layer, and it depends also on that parameter, which takes values, and we can optimize over that. Okay, and at this point, we can start seeing the advantages of this versus that. Firstly, you can see that the terms here are both equally scaled on the functions. So before I said that the reason why you get vanishing gradients is because you have one function inside another one, and then that is going to make things very nonlinear, and is going also to cause vanishing gradient problems, and this poor scaling of the gradient. Okay, that's not happening here anymore because f has exactly the same effect as g, in that it is, both of them are as if they were the last layer on their respective networks. So if you change a parameter in f here, the effect is smaller than if you change the same parameter here, because this automatically is going to change this term here. That's one thing that we gain. Another thing is that the 2 functions get uncoupled, and that's going to simplify the optimization later. Another thing that you get is that now you may not need to use derivatives at all. If you have them, of course, you may use them. But imagine, for example, that f here is a function that is not differentiable. For example, imagine that it is a layer in a neural network where the nonlinearities are step functions. So you cannot take derivatives with respect to that. Well, then that would make it impossible to use the chain rule here, because you could not backpropagate it. But here, that problem is still there, right? The function f has still a step function, but you may be able to train this shallow network using, for example, a perceptron algorithm, which can deal with that kind of thing. Or imagine that this is a feature selection step, which what it does is it selects k features from your input, and then the values of those features go to the second layer g. There is no way to take gradients there because that function is not that it is discontinuous. It is that it is not it's not discrete. It's discrete. So it's not that it doesn't have derivatives. It's a discrete function, and it lives in a combinatorial space, so you cannot do backpropagation there, you cannot compute any gradients. But here, that function, while still being discrete and it is there, it turns out that you can solve this for reasons that if I have time, I will explain to you later. But basically, by partitioning this into the two layers separately, it may be possible to use algorithms for training individual layers that already exist and that may or may not use derivatives. And that would not have been possible in the first function because it is all composed. Okay, so optimizing the original function, as I said, will have the problem of following this convoluted path in the parameter space. And then in this new space, what happens is that you have extra space. These are the new coordinates, and you can move in that space by violating the constraints, and that can allow you to take shortcuts from the original point, the initialization point, to the minimum. So you don't have to follow the complicated path, which would mean that you respect these constraints. You violate them, that's okay, with penalty methods. That's why penalty methods are useful, because they don't have to approach your solution from the feasible set. They can take steps across the feasible set, the infeasible part of the problem, and then you may be able to solve the whole thing more efficiently. Okay, so that is one key aspect of this algorithm. And violating these constraints means that these two functions are mismatched. They are mismatched during the optimization because the output of the first layer does not match the input that this second layer expects, but that's okay. It's okay during the optimization. Upon convergence, of course, you want this to be satisfied, and it will, but it doesn't have to be satisfied all the time, and there are computational gains there. Okay, so I haven't told you yet actually how to optimize the whole thing now. So let's look now at this and how to optimize that. You can see, because of the separability structure that we have created, that alternating optimization is going to work very well. So what we do is that we alternate between the functions and the coordinates. If you fix the coordinates set, if you fix all these parameters here to the values that they currently have, and you optimize over f and g, you get one problem here over f, and one problem over g, and one problem over f, which are these two. They are completely independent. And you optimize them, and you can see that what they are doing is training the layers independently. You see what I said before about fixing one layer and then training the second one, giving the outputs of that. That's exactly what is going on here. But we are not introducing that on purpose. It is just coming out as a product. Okay, so solving these problems may be done, as I say, by using derivatives or not, but basically what you have to do is find a function g here that fits these inputs to these outputs, and find another function f that fits these inputs to those outputs, and that's it. And as I say, in many cases, if, for example, this was a linear SVM or a logistic regression, and this is a linear function or a real basis function or whatever, you may have already algorithms that solve those individual problems, those shallow problems. These problems are shallow in the sense I described before, and the only thing that you do is simply reuse those algorithms. You don't have to code anything. Reuse those algorithms and solve the problems. Okay, now this is for set fixed. Now if we fix f and g, here we fix these two functions, and then we optimize over set, we have a lot of sets here. We have one per data point, but you can see that they appear additively as well. So each problem, each set for each data point becomes a subproblem. That means that you have, instead of having a very big problem with all the sets combined, you have n problems, which are separate, one for each set. And it looks like this. So this part here is the problem for one particular set n. Okay? It comes just from here by removing the summations and focusing on one of them. Okay, this often is a small problem. And it has a very, very special form, if you look at it. It has the form of a proximal operator, in case you have heard of that. These operators are very popular these days in non-smooth optimization. They have this generic form here. So this is indeed a proximal operator. And what it is telling you is, find me a value for this coordinate set which is close to whatever this value is. This is a number because f is fixed. So find me a set which is close to that value, and at the same time, it is able to predict its label 1. That's all that you have to do. And this is a problem that has to be solved. So this is a new thing that was not in the nested problem. This you have to solve, but it is not very complicated because here set appears quadratically, and here it appears within a single layer network. So this problem, this part here is actually very similar to this other thing here, only that instead of training optimizing over the parameters of G, now I optimize over the inputs of G. So it's really a symmetric problem in that sense. And many times the solution of this, depending on your model, it can be either in closed form or it can be very simple by solving a linear system or something like that. Usually it has the form of some kind of projection. It has a very powerful geometric flavor, this kind of proximal problems, basically projecting this value onto a certain set depending on that function there. Okay, but this has to be solved, and the role of this step, of course, is to coordinate the layers that you were training before independently from each other. Because if you just do that, then this would not converge. It would just be the original, the layer-wise thing that I said before. This step here is the crucial one, which takes care of making sure that things glue to each other. And as the penalty mu goes to infinity, then the constraints here are eventually satisfied. Okay, so then the overall algorithm looks like a coordination minimization algorithm, in that the minimization step fits the layers, minimizes the error there individually, and the coordination step coordinates the different layers. And that is similar to the EM algorithm, that the M step in the EM algorithm fits each, like for a Gaussian mixture, for example, it will fit each Gaussian independently of each other. And then the E step, the probabilities there, the posterior probabilities, will make sure that all these models are actually coordinated, and the whole thing converges to something which is an optimum of the original problem. And here I want to emphasize that even though I am doing alternating optimization here, these two steps, that is not the same as the pure vanilla alternating optimization over layers in the nested problem, which you can also do. That means that you fix F and then you train G, and then you fix G and you train F. That would be alternating optimization. That's not the same as what I'm doing here. Because if you do that, then when optimizing over F for G fixed, you still have to use the chain rule to compute the derivatives of F, which is inside G. Otherwise, so it's not like fitting F by itself, as if there was no G there. F is embedded inside G. So this alternative optimization is not like layer-wise training. Okay, so the algorithm, I explained it to you for just one hidden layer, but it generalizes to k layers. The equations are more complicated, but it is just the notation. The nested objective function here would look like this. There are now k hidden layers. You constrain in the same place. Now the variables in this particular formulation here, you introduce variables at every layer. So the output of every layer, you use variables there. That gives you the first layer and the last layer. You bring them to the objective quadratically, and then you have your quadratic penalty. And then you apply alternative optimization, and again, the W step looks like before. So each layer is trained independently of all the others. And the set step now involves, instead of just two terms, it also separates over every data point, right? Every data point separates. But for every data point, instead of just two terms, you have one term for each layer, which would look like this. And set always appears either quadratically or inside the function of one of the layers. So it is basically the extension that one might expect. And also, although I'm not going to go into it here, but you can use other loss functions instead of quadratic. There is no restriction on the connectivity of the layers. They don't have to be sparse or anything like that. They may be, but they don't have to. You can also have constraints in your original nested problem, as for example would occur if this is if the last thing here is an SVM. You will have some constraints in here. That's okay. You can also use that. You can apply this idea to substituting sub-expressions in the constraints as well. You can use also penalties here which are not quadratic, etc. So there are many possible implementations of this algorithm. The algorithm converges, and here are two theorems about that. The first one tells you that the nested problem and the constraint problem are equivalent, which intuitively looks true. You can prove the KKT conditions are in a one-to-one, the minima, maxima, and saddle points are in a one-to-one correspondence with each other. And then the quadratic penalty objective function that we get, what that theorem tells you basically is that if you, at each step, you minimize the function within a certain tolerance, and that tolerance goes to 0 eventually, so you're minimizing better and better the function. And if you drive the penalty parameter to infinity, then you will converge to an optimum. So you follow a path in this augmented space that converges to an optimum, and that path depends on mu. Okay, so now to summarize this, the design pattern, if you want to apply this algorithm, the design pattern is as follows. You write your nested objective function, first of all. Then you look at it and identify sub-expressions inside it that are nested, and then take them out by introducing auxiliary coordinates with equality constraints. And you can do this in different ways. Usually there is an obvious one, but there may be more. And then you apply the quadratic penalty or the augmented Lagrangian to that. You apply alternative optimization to that, and that gives you the two steps. Over the weights, over the original parameters, which typically will look like simply training the individual layers using existing algorithms. And then the set step, which the form of it will depend on your problem. And that has to be solved. I already have solved it for a few different forms. And then the effort involved to get this to work is similar to the effort of deriving an EM algorithm, where you have to write your model and your likelihood function. You have to look for the hidden variables there, the missing data. And then you have to, you would write the complete data log likelihood, and from there obtain the E step and the M step. And then you have to solve the M steps, which are optimization problems. So very similar to the kind of thing that happens here. Yeah.
In the case that you have a Lagrange multiplier, you train Lagrange multipliers in M or CS directly, which one? Because the Lagrange multipliers also need to be.
They are trained outside in their own loop. So usually when you have an augmented Lagrangian, what you do is you iterate over the primal variables and then over the augmented Lagrangian. So all the alternative optimization and all that will be independent of that. And the optimization over the Lagrange multipliers is just a fixed form. So you set the Lagrange multiplier to a certain thing that depends on the constants. Yeah.
So in whatever you have tried, how often do you need to update mu, like in the sense that how many times do you have to do this entire procedure?
Yeah, so to be perfectly honest, updating mu, like in any quadratic penalty or augmented Lagrangian method, the penalty parameter depends on the problem. But you do have the guarantee that if you drive it to infinity, you will converge, right? Practically, of course, I understand. It may depend on the problem. What I observed is that in most of the problems that I have tried this so far, which are, I will show some here, they are quite different from each other. If you just fix mu to 1, you already will get a very good solution, just with that. And if you want to converge, then yeah, mu has to go to infinity. Also, I should say that for some problems, I think that you can prove convergence to a minimum without driving mu to infinity. But these are special. Okay, so I'm going to show you now one example here. This is applying this algorithm to a deep net here. The net has takes as input some handwritten digit images, and it has several layers here. It's an autoencoder, so it tries to reconstruct the image from its input. It has a hidden bottleneck here of 20 units, and they are logistic layers. Okay, so of course you can train this with SGD here, stochastic gradient descent, or with conjugate gradients or whatever, and you will get some performance that may be more or less good depending on how you do things, on how you choose your learning rates and all that. The red curve here is what you get with this Mac algorithm, where I introduce auxiliary variables at each output of the sigmoids there. Okay, so the markers that you see here, in the Mac algorithm, each marker corresponds to one iteration, while for SGD, each marker here corresponds to 20 passes over the whole data. And for conjugate gradients, each of those corresponds to 100 passes. So this is telling you that each iteration here has a very powerful effect on decreasing the objective function, which is caused by the fact that separating all the layers makes changes to all the weights at once in every single layer, large changes to that, which is not easy to achieve with backpropagation for the reason of the vanishing gradients, as I said before. Later, I will show you how this parallelizes. This will be the result of running this same thing here with 12 processors, so it becomes several times faster, 8 times faster or something like that. And these other two curves here are what you get using the Mac algorithm, but if you use mini batches. So in here in SGD, I'm using mini batches. And for this curve here, I am doing batches. Is the batch mode, which of course is not going to be very good. If you use mini batches also in Mac, in the W step, then you can accelerate this considerably, and this will be this curve here. And that other one there is the parallel version of that one. So basically what I'm saying here is that the naive implementation of the algorithm using, in this case, Gauss-Newton optimizer for the W and the Z steps, which is, they are big steps, batch, and done exactly, basically. That takes a long runtime per iteration, as you can see here. That can be done much faster if you just apply cleverly some standard optimization techniques. But each iteration decreases significantly the objective, and then the runtime itself can also be made smaller with clever optimization, well-known standard optimization techniques. Okay. So as I said, one thing that we observed in general is that even for mu equals 1, you can get a pretty good net in just a few iterations. And then you have to increase the penalty parameter to achieve eventually convergence. Okay. I only have 5 minutes left, so I'm going to hurry up with a few important things now. I'm going to skip some things here. Okay, the way of introducing auxiliary coordinates, as I say, one way is at each layer, but that's not the only way. For example, you don't have to introduce coordinates at each layer, or you can introduce them before the sigmoid, in which case you get a linear step, a linear W step, for example. There are many variations there. You can even redefine set over the optimization, because it is just a mathematical construct. And let me now show you, I want to show two other things before I finish. One is how to do model selection on the fly with this same idea. And the other one is how this applies to large-scale models because of the distributed nature of the algorithm. Okay, so firstly, model selection on the fly means the following. If you want to do model selection, let's consider model selection criteria as an example. This is not necessary, it's just to illustrate it. Model selection criteria like AIC or BIC. What these do is that they will take your nested objective and add to it a term which basically penalizes the number of parameters. It counts the number of parameters and multiplies it some number. So it is additive on the number of parameters of each layer. Now, if you want to minimize this, imagine this is a deep net, for example, and you want to penalize it with something here and minimize that, then you will have to choose a number of hidden units, etc., train the network, and you get one result. Then you choose a different number, etc., and repeat. And if you have k layers and you have m hidden units in each layer, then repeating that would cause you to test an exponential number of models, m to power k. M for the first layer, m for the second layer, etc. In this algorithm, because this cost here is separable, then if you just apply the algorithm to this function here, this thing here is only going to appear in the W step. It is not going to appear in the Z step because it is a constant. It only appears in the W step, and in the W step, it is going to separate as before, because over layers, I mean. It is going to separate because I am saying that this is a separable function. So what happens is that within each layer, you can do model selection on that layer. So that means that you are actually doing model selection on everything at once, but it separates. Because it separates, then instead of having to do m to power k models, you only have to do m times k models. M for the first problem, independently of everybody else, m for this other problem, independently of everybody else, etc. So there is the separability there is again helping us to break an exponential complexity into a polynomial, a linear complexity. And besides, the models that you have to train in each layer are shallow. So you just train this layer, which is a shallow model, and train it m times, and pick the best one. So this allows us to do model selection on the fly. And I am going to show you an example. In here, this is another neural net. This is made up of basis functions, real basis functions now. And there are 1, 2, and 3 hidden layers, but I only introduce variables here. And then I'm going to do model selection over the number of basis functions here and the number of basis functions there. So if I have m here, m1 and m2, then I will have to test m1 times m2 models. But in this algorithm, what you do is that whenever you train this layer in one of the W steps, you can, if you want, you can do model selection. And you can choose how many functions to put there. You try a few of them, pick the best one. And then you continue with that for the next set step. So if you do that, then what happens is the following. This is the objective function and how it decreases over iterations. And between green dots here, we don't do model selection. So we just train the model with the architecture as it is, the number of basis functions. We refine we optimize over the parameters. But then at every green point here, we do a model selection step where we decide how many basis functions to use in each layer. And then you can see that there are these sudden decreases, which are caused, in this case, you can see that I started with 1,368 basis functions in each layer. And then here, at this point, I moved to a model which only 700 and 150 functions. So this model has a far lower cost in terms of the number of parameters, and that's why there is this drop here. And while I'm doing this, I am always minimizing the function. So this is not a heuristic or anything like that. This is actually minimizing the true objective plus the penalty cost that you had, only that you don't have to do this model selection at the end once you have trained and repeating it for many nets. You can do it on the fly. Okay, and then I wanted to mention that this is also very convenient for large-scale problems because of the parallelism that you already must have noticed before. So in the W step, I already mentioned that all the layers separate, but also if you look at the form of the layers, like here, because this is a quadratic function, then the quadratic function also separates over coordinates. So this here, for example, is the sum over the first coordinate, the second coordinate, etc. And those are going to separate themselves in a neural network, for example. So that means that you not only get a collection of problems that are separable, independent from each other per layer. Actually, within each layer, all the hidden units, all the weights that enter a hidden unit, they themselves are separate problems. So there is a lot of separability arising from the algorithm. And the model selection steps also separate. And then in the set step, as I mentioned before, it separates over all the points. So this allows you to map this to a cloud computing architecture, because you get, at each step, you get lots of different separate problems. And this is, for example, what happens if you vary the number of processors in the problems I mentioned before. And this is how the speed up grows. It grows nearly linearly. And the only thing that we had to do to make the original code parallel was to change 2 lines in it from 4 to par4. And these are the lines of the W step and the Z step, so that each iteration of that is sent to a different processor. That's not the best way of doing things. It would be better here to use MPA or something like that, but it already shows you that the separability does work. Okay, so I'm out of time already. I'm going to, well, this can be applied to lots of problems. It's not just about deep nets. You can do best subset feature selection here. You can apply this to joint dictionary and classifier learning. You can train a neural net followed by an SVM or a decision tree. You can do things that nobody has done before that I know, because it was not possible to apply a standard gradient training to that. So in conclusion, what the method does is to optimize jointly a nested function over all parameters. And what it does is to restructure that problem in a way that affords you separability over many of the parameters. It results in these two steps. One is a step that trains layers independent from each other. And then there is this other step which is crucial to coordinate the layers so that you achieve guaranteed convergence to a minimum of the original nested problem. The algorithm is, once you get the hook of it, is very easy to develop and basically results in something that reuses existing algorithms already. It has embarrassing parallelism, can work with non-differentiable or discrete layers, and can do model selection on the fly, which basically is a discrete optimization. It's one example of a discrete optimization that does not rely on gradients. Okay, and more generally, I think this could be developed into a software tool that allows somebody who might not be an expert on machine learning to pick models from a GUI interface, for example, and put them together like a Lego thing. And then the tool would select automatically the way of introducing the coordinates. It would take the existing algorithms from a library, and it would compile the program into a target multiprocessor architecture without the user having to do any of that. And this would allow users to develop complicated, sophisticated models simply by combining things. Okay, so as I said, this is mostly unpublished, but here are some references about the work. And that's it. Thanks.
As you said, actually, this seems kind of similar. Some of the ideas are kind of similar to EM algorithm.
Yes.
You can see this z variable as the latent variable, actually,
In a sense, but there is nothing probabilistic here.
Yeah, but you can assume you can take some Bayesian approach and assume some prior over the end, then you can do the EM step.
It could be. So I certainly think that there are relations with probabilistic formulations of this, and you can regard, what is it? The set step here, in fact, as fitting something with a prior on those variables that you say, in this case a Gaussian prior. Yes, it could be. But everything here, I don't impose what comes out. The only thing I start here is just the introduction of the variables at certain places, and then everything else just comes out automatically.
Have you tried to push this method to see how many layers it takes before this method breaks, if any? So for example, people who work on deep learning typically restrict themselves to 3 layers because even with their advances, they can't really train reliable models beyond 3 layers.
Yes. We tried it with up to, I think, 14. With 14 layers, it works fine. It gets worse the more layers you add, but it does work quite well, and you see changes to all the parameters with a lot of layers. Yeah.
This is very elegant stuff. I love simple. I was thinking, where might things break down? And in regions where, let me see if I have this right, where the value of f lies near a singularity of g, that's where you get more error. And I think the penalty is such that we'll focus on those things. So is there anything else that would help to do with those points, or does it just all come out automatically?
I'm not sure what the singularity would be here that you.
Well, if there's sort of a discontinuity in the function g, such that having the mismatch between the coordinate variables
Yeah, I haven't thought about that, I have to say. But it would seem to me that even if that happens, if that happens, that already would be a problem in the nested case, I would say. Right, because in the nested case, you have the original function applied, and then you apply g, so if there is a singularity there, it is going to affect the function in the first place. But I don't know what to say about that.
So do you see this as the future of training neural networks?
I don't know about that, but I think that there are a lot of opportunities to apply this to models that already are being trained in certain ways. This could be a better way sometimes, I don't know. I don't think this solves every problem. But also I think that this allows you to train things that are not possible to be trained right now, like the feature selection, for example, searching over features and classifiers at the same time. I don't think that is easy to do otherwise.
So what are the drawbacks? Why would this not be the thing to do? Because I mean, you can put any set of layers together, decision trees, SVM, whatever.
Yes.
And you seem to be able to parallelize everything out. And
well,
where does this break down?
Yeah. Firstly, it doesn't solve every problem because you need to be able to make sure
the prox operator is
that you can solve this part here and this part here. This part generally is not a problem because so you must solve this one here. And this may be more or less complicated, but as I say, it is often simple. The other thing that is more problematic is, in my view, is that eventually the algorithm slows down when converging. Most algorithms slow down anyway, because with large scale problems in particular, it is impossible really practically to do much better than linear convergence and very slow linear convergence. But with this algorithm, you will get that kind of slowing down because alternative optimization is an algorithm that tends to have that behavior. So alternative optimization algorithms are extremely popular, like EM and many others. They are extremely popular because they are so simple to apply to anything, and they converge easily, right? And you don't have to code much. Super simple, they don't break. They make a lot of progress at the beginning, like EM. Usually you start from some random value, and in one or two iterations, it gives you something that makes sense. But then it will converge more slowly.
First of all, this objective function that you have is root error or it's the square error? I mean,
this was the squared error.
Okay. So there, basically the rate is something like a square root 1 over root t actually, because it goes like this. Because in convex optimization, it is 1 t actually.
Right. So this is non-convex. Everything here is non-convex, and the rate of convergence. Well, bear in mind that you have to drive mu to infinity. So how fast you converge, firstly, will depend on that. And for a fixed mu, where you will have to solve this problem here, then you have the alternative optimization. That's where the alternative optimization occurs, and the rate of convergence of that will depend on, I think, how you do that. So I'm not sure what to say. All I can say is that I think the rate will not generally be better than linear, but not sure. Yeah.
So another question that I have is that in EM, how your approach works with local minimum? Because in EM we have this good property that we observe, actually there is no theory, but we observe that the algorithm just pass some of the local minimums and usually converge to a good local minimum. So is it also the case here?
I have heard that kind of comment so many times that such and such algorithm seems to get rid of local optima. I don't trust any of that. I think that the local optima are a property of your function. They are there. You cannot, and then depending on where you start, I think that's more important than anything else. Depending on where you start and the algorithm, certainly what kind of steps it takes, you will get to a certain local optimum. But I would like that this finds good optima. I don't think it does. I don't think EM does. Everybody knows that if you train with a Gaussian mixture, you're going to get bad local optima with EM. It's a well-known problem.
It can start in local optima, but because it is not moving in the direction of the gradient descent, so sometimes actually this how do you call it, this upper bound approximation that you minimize in EM.
It could be, but just because it doesn't move in the direction of the gradient doesn't mean that you're going to end up in a better optimum. So Personally, I don't trust much. I think it is mostly an anecdotal observation that sometimes an algorithm tends to avoid local optima more than anything real. That I would very much like that to happen, but I don't think. And I am quite sure that EM and alternative optimization, at least for some models, it can convert to bad local optima just like any other algorithm. Yeah, so he was first.
Do you think that your method can be applied to energy-based models where there's no like nesting? It's like an example of a macro-random filter.
No, the whole thing here is that you have to have some nesting because it relies on the introduction of those variables. If you don't have nesting, then you may be able to apply some kind of transformation there to the problem, but I don't think you will be able to apply this one here.
You mentioned that Lagrange multipliers make things better.
Generally,
the
yeah.
results that you showed using them, and what is their effect just to speed up the convergence?
I actually didn't show any results. All the results here were with the quadratic penalty. But yeah, but the comment I made was general. So not for this particular method, but in general, the quadratic penalty method is considered inferior to the augmented Lagrangian because the augmented Lagrangian, it is optimizing over the primal variables and the Lagrange multiplier estimates, both at the same time. So it is able to get closer to the objective function with less ill conditioning than the quadratic penalty. That's usually the reason why it is preferable.
Does that translate to faster convergence?
Yes, yes, definitely, because when mu increases here, you are going to increase the ill conditioning on this problem. This happens with any penalty method. The higher penalty, the more ill conditioned things get. And with the Lagrange multiplier estimates, then you can get to the same distance, basically, to the optimum with a smaller penalty parameter than otherwise. So it will be easier to optimize. Yeah. But that's a very general comment. In each case, you will have to see exactly how things pan out with the model that you have. Yeah.
So one question is that that mu here, there, like I'm a little bit concerned. It's true that it's the regularization parameter, right? But
That was just an interpretation. This is not a regularization of any kind. This comes out mathematically from the way the algorithm is derived. In other words, this is not something that you have as a user. You say, I'm going to put this and I'm going to regularize more or less. No, this is the result of solving this with a quadratic penalty. It's just a way of solving that problem.
right, but like my question is somewhere else. My question is that the scale delta. So if you go 2 slides forward, where you had me? Oh, here. Yeah, right.
Here.
So the first one is in scalar. Yn is scalar and Gzn is scalar, right? But like the second one is like a vector norm, right?
No, this is a vector norm here, right? And this is another vector norm. These are the outputs. This is not necessarily a classification problem. In classification, yeah, in classification this would be, but you would not put there probably this. You would put some kind of entropy or something like that.
Okay.
But anyway, what was your question?
So I was just thinking that like the scale of these things, especially when we have like multiple layers, is going to be important. So mu1 and mu2, for example, if you have 2 of them. Yeah.
Okay, that's a good point, indeed. So yes, and I think that when you have many layers, using different penalty parameters for each layer probably will improve convergence if you do that cleverly. Certainly, it is not going to crash the method. It will converge because look at the following thing. You see how this is defined, right? Okay, now imagine that for the constraints on a different layer, I multiply this times 10 on the left and on the right. Nothing changes, right? I can multiply on the left and on the right times a constant that constraint, and it is still an equality constraint. But when it goes inside here, that will carry the 10 squared. You see, so I can certainly use different weights on different layers, different penalties basically, by essentially redefining the constraints here in that way. They all solve the problem, but of course some will be better than others. And I do think, although I haven't explored that in detail yet, I do think that there probably is an optimal way of introducing those penalties that depends on the depth of the layer.
At the beginning, you said that most of this is unpublished, but you would give some pointers at the end.
They were at the end. They were here. Most of the stuff is in here, much of it. Yeah, and then some will be, as we put it, it will be online sooner or later. Any other question?
So this seems to have worked well on computer vision problems, and are you trying it on other large-scale language? And
I am actually working on implementing this for neural networks in large-scale problems with a Google Award, where we have a data set. This is purely distributed, and we have bits of the data set on different processors, and the data never moves out of there. The only thing that moves are parameters. That's the only way that you can achieve pure scalability to large problems. Yeah.
so that's why it's related to mini batching.
Yes, in that case, you are going to have to use mini batches because you are not ever taking a step on the whole data because the data is all over the place. Yes. Thank you.